Hi, everyone. Good evening. Y'all here? Y'all here? Okay. All right, nice. So lastly, we were doing some total internal reflection type questions, right? We still have some more to do, but I just want to run through some of the theory here, right? Did I ever did I ever send this on the group, this manual? I think I may have sent it. I'm gonna just send it back, right? I think I would have sent it in the earlies. Yeah, I sent it in October, but I will send it back again, right? Like, just a nice little manual with some notes, something that I can look over. All right. I send it back here again in area. All right, so we should remember about total internal reflection, right? All those things should be familiar to, right? Let's just run over a few of it and look at some examples of some applications of it, right? So we know it's critical angle. Critical angle is when the angle of incidence is 90, right? As you would see in the second example, right? Right, here's what will normally happen in refraction. Here is when it reaches the critical, and here's when it's more than critical. You will notice they said that total internal reflection happened here, right? So I was more than C. And what was the next reason again? What was the next reason why what was the next reason why total internal reflection happened? Anybody remember? Right, very good, Tion. The ray was in the denser medium. So because the ray in the denser medium, which is the glass here, and this value here is more than the critical angle, we know that total internal reflection will happen, right? So here are some applications, right? One of the applications is optic fibers. Optical fibers are used in bundles, right? Before we read it, just take a look at what happened in here. You have this light ray. Remember, light ray can only travel in straight lines, right? But because you have this particular material that allows for total internal reflection at all the points of incidence, what you have is you could take a light ray and allow the light ray to travel in a path like this, right? Because of course, if that wasn't there, the ray would have just gone in a straight line or refract out, right? But you would recognize that each of these points here, you have total internal reflection happening. So you could take a light ray and you could allow the light ray to travel any type of path, straight line, curve, anything you want, by using these optical fibers. So the optical fibers are going to the note, right? Optical fibers are usually held in bundles to carry data at high speeds. They may be used as an endoscope, an instrument that is used into the body to view internal parts. Light is shot into the fiber and is reflected back up to the detector with images. Right? You'll realize this part in red here. The incident ray is shot at an angle greater than the critical angle so that it keeps reflecting over and over inside the fiber. And of course, we know the fiber is the more dense material, right? Optical fibers are made of a core of high refractive index surrounded by cladding that is less dense than the core. Another example of total internal reflection would be the use of road reflectors, which are usually right-angled prisms that reflect light back to the vehicle. And you will see the example there. You all remember doing this on Saturday? Yeah, good. Where we bend the ray through 180 degrees here. And exactly what they said, this is the principle of a reflector. So your light coming right back at you, right? So you'll be able to see at these edges, right? Like those reflectors on the road. It's just basically how it operates. Right. So next time you're on the highway, you could come out and you could go on this side and take a look at the reflector. And you would see the prism design like that. All right, Tanya? That's your homework, right? Right, go on the side of the highway and take a look at the reflectors. You'll take a picture and bring it back for the class. Don't forget Tanya. Oh, shucks, I didn't add the other boy to the class, Ijaz. Okay, so these are some applications of total internal reflection. Right, there are some, there is a next popular example. For those who may have a pool, right, or looked into a pool. If you look at a light at the bottom of the pool, right, we know that the light is a bulb and all here should have light. But if you look closely at it, you would recognize that there are some points where you're not seeing anything. So it might look kind of donut shape. So you might see light all here according to the angle you look at, right? But in some parts, you're not seeing light. And anybody could explain why? So you would see light from all here, all around here. But there are some particular parts that you're not seeing light from. And sometimes the other way around, right? This is the whole thing. And you will see light all here, but you're not seeing the light on the outside. Anybody could explain what happening at these points here? Why it is there are some points that you're not seeing light coming from the bulb. Anybody? Think of the topic that we're doing. Right, yeah. That's a very simple example. Because of total internal reflection, some of the light not coming to you. So it's like this little part in the middle here, I will change the color. This little piece in the middle here, those light rays undergoing total internal reflection. Remember, for you to see something, the light has to come to your eye, right? So if no light coming to your eye, then you wouldn't see it. Okay? For you to see your phone in front of you, light has to bounce from the or come from that into your eyes, right? If you were to take off the light and look at something, well, take off your phone, of course, and try to look at an object in your room, you wouldn't see it, right? Because there's no light to bounce off of the object to come into your eye. All right, so you need to see that light. So all these spots here, they would have undergo total internal and the light not coming into your eye. And some of them just at the wrong angles, so you're not seeing it. Okay, so those are some applications. They have total internal reflection. We know all this about refraction already. These are all the formulas for refraction. And we were able to do, I'm not sure if I gave you the wavelength version, right? But it's add the scene as well now. For total internal reflection, add the scene here as well. I gave you the sine theta 1 and sine theta 2. I gave you the speed and medium 1 or speed and medium 2. I'm not sure if I gave you the wavelength. Right? So these are 3 ways to find refractive index. Right? Speed and medium 1 over speed and medium 2. Wavelength and medium 1 over wavelength and medium 2. Right? Those are 3 ways that you could find refractive index. Right, one thing I want to point out as well, look at this ray down here, right? Look at this ray, it leaving medium A and going to medium B. So if you had to guess Nuria, Which of these mediums doing the refraction? Medium B or medium A? Which one doing the refraction? Look at the way it's going up this way. Which one doing the refraction? Medium B or medium A? Yeah, correct, medium B. Because the ray has to go into medium B. So medium B doing the refraction. So sometimes you would see this, the refractive index of B with respect to A, right? Because if I were to change the medium A, although it going towards B, the refractive index value will change slightly, right? So it's important that you know which one it's coming from, right? That's why sometimes when you see the refractive index of glass as 1.5, right? What that really saying is that is the refractive index of light as it goes from air to glass. So this is the refractive index of glass with respect to air. All right, so it's something important to remember, because if I were to put glass here and water here, the refractive index would change slightly, right? Because these values would change slightly. Okay, so I want you to remember that, right? It's always important that you know what refractive index value you have. Okay. Right, and we'll remember we did an experiment already, right? And that's something that we're going to be doing a lot of. We're going to be doing experiments every now and again on the ones that we could actually do in the lab. So you get a little practice with doing the experiment and plotting your graphs and doing your calculations and things, right? So when you do it in school, it'll be easy. Right? You have your refractive index, you have a critical angle. Oh no, we're not doing lenses as yet. Okay, so those are the things that you need to know. So far we looked at two wave phenomena, reflection and refraction. Anybody remember the next one, the next two? What are the next two wave phenomena, things that waves undergo? Diffraction, nice. And one more thing. Waves undergo diffraction and one more thing. Interference. No, we did reflection already. Interference. Good job, Severa. Right. Before we go and take a look at interference and diffraction, right, I just want to point out one more thing. Right, this one here was that was basically the glass block experiment, right? Where the light was refracted and the emergent ray, right? The emergent ray was parallel to the incident ray, right? And we said that the deviation from here to here, deviation from here to here is called your lateral displacement or your angular deviation. Some people put it as an angular deviation. All right. So it's just something for us to remember. Right. There is one more phenomena that is popular in refraction that I forgot to mention. It's called the dispersion of light. Right? You all may have done that in Form 1. Right? It's called the dispersion of light. To be exact, white light. Is the dispersion of white light. So if I take a triangular prism like I have here, right? That's a triangular prism. And I take white light, right? When the white light goes through the prism, the white light is going to split up, right? And you all should know that white light is made up of all these colors, Roy, G, Viv. And each of these colors has its own wavelength and travels at their own speed. So when they undergo refraction, they all behave differently, right? We know red has the highest wavelength, and the last one is violet, has the smallest wavelength. And then, well, you have orange, yellow, green, blue, indigo, and violet, right? Those are all colors. And when all these colors, each of a different speed or a different wavelength, pass through a triangular prism, they all undergo refraction, right? And they all give you a different angle of refraction. And as a result, they will split up, right? So it's like a race. Each one of them traveling at different speeds. As soon as the race starts, right, they all will travel at a different speed, and they will no longer be in a straight line. There might be something like that, right? Red is the fastest, violet is the slowest, right? And they will split up. And as a result of splitting up, what you will observe here is called the dispersion of light. You have white light being split up into all its constituent colors. Are you okay with that? You all okay with dispersion of light? Go it over, right? So remember that white light is made up of all those different colors: red, orange, yellow, green, blue, indigo, and violet. Those are all the colors that make up white light. They're all mixing together and they form white. And what will happen now is that each one of those specimens of light or parts of light have a different wavelength and a different speed. So when they go into the glass, they would undergo refraction. And because of the refractive index of glass, it would cause each of those colors, red and orange and yellow and all the others, each one of them to change the speed. So imagine they all at the same speed here. But then when they undergo refraction, they all start to travel at different speeds. And because of that, they will split up, just like a race. The fastest will be out in front, the slowest in the back, and everybody else split up, right? And what you have there now is white light being broken up into all its colors, from Roy, G, straight down to Biv. And that is called the dispersion of light. You okay with that? Right? And again, the main reason is because each of these specimens, each of these parts of light have different wavelengths and different speeds. Okay? So that's the dispersion of light. Let's see what they said here. White light undergoes dispersion in a prism and splits into its colors of a rainbow as it refracts. Red has a longer wavelength than violet, so it refracts less, and so on, right? Right, so you have all those there. And well, here's an example of refraction as light goes from, as a ray of light goes to different depths. Remember, deep and shallow, right? Right, those are different densities. Sometimes instead of just drawing the ray, they ask you to draw the wave front. That's all these waves here. All those waves, they are the wave front. Okay? So you got to remember, you got to be able to draw them like that. Right? Always remember that your wave fronts are perpendicular to your ray. So if I draw a ray like this, my wave fronts are perpendicular and they're equally spaced, right? Because each one is a wavelength. You will notice that the wavelength, as it goes from deep to shallow, the wavelength gets smaller. Okay? As it goes from shallow to deep, well, the wavelength will get a little bit bigger, right? And they bend away, right? So to show you 3 different ways we could draw them, right? Well, 3 different directions, right? And as we learned last week, once a wave travels along the normal, they're undeviated. Okay, some nice little diagrams there to remember. Right, and here you have 2 examples of refraction again. Right, mirages. A mirage occurs mostly in hot places. And the main reason for that is that the air travels through different densities. It have the hot air and the cooler air underneath. Right, so you would recognize that here, instead of the ray going in a straight line, the ray undergoes refraction. So you see that bending? So because the ray bend, watch what the person really seeing. The ray really coming from here. The ray really coming from top here, but he not seeing that. because the ray underwent refraction, he's seeing the ray coming from underneath. And when you draw it backwards, he's gonna see the object looking like that. So what he's seeing there is the refracted version, is the refracted ray coming into his eye. And the object he's seeing there is a mirage, which is not really there, right? The mirage is up here. Okay, so the reason why the ray is bending is because there's a different, the density in air changes. When one part hot, that less dense, and when it cooler, it more dense. So because of that change in density, the ray undergoing refraction. All right, the difference in density is important to note that the heated air and the cooler air would be considered two separate mediums. As a result, light would refract or bend as it moves from one to the other. As a result, it is as if the ground acts as a mirror, right? Showing a reflection in the sky. All right, so you may have noticed mirages, something like when you're on the highway, right? You might observe mirages there, right? And then you have something called polarizations that help reduce glare. All right, so I could read up on that one. Right, so those were the things that you need to know about refraction, and we did reflection already. Right, we have two other things to undergo. That's diffraction and interference. But before I interfere with this question, there's something I want you to do for me. I want you to try this question, please. Right, there were two that we had to do. I have to get back my booklet. I can't remember the the picture here. All right. This was one that we were supposed to do last class, so we didn't do it as yet, right? All right, just do me a favor now. Do this, please. All right, I'll give you 5 minutes. How much marks for it? 2 marks? I can't see that. How much marks are they saying there for that? Oh, yes, 12. Okay. Go ahead. Try this some. Right, just please remember this little rule here, right? For the maths people, or people who don't like maths and you're learning your maths. Whenever you have two parallel lines, right, these alternate angles equal, right? All right. So because we're online, I can't really see books. So of course, work it out first. And I want you for part 1, all you're doing for me is sending the angles, right? And part 2, the same thing, send your answer. Go ahead. I'll give you 6 minutes. Do that, please. Don't forget to send your answers earlier. Right, start sending the answers that you have. Right, I only have one answer so far. Good job, Tion. We'll work them out just now. Another again, sure. Did you get stick? You got the first one? Yeah, so they give you the refractive index here, right? Okay, well, tell me how you got the first one, huh? For sine theta 1. What formula you use? You could use your audio so you don't type out all of this, huh? How you got the first one there? Okay, right, good. So you use refractive index is equal to sine I over sine R. And they gave you the refractive index up here for medium 1 from A, right? So from A to medium 1, 1.2. And you have sine I. I is 60 degrees, they give it that here. All over sine R. And then you cross multiply. Right, like what we did last time, cross multiply and make sine the subject, right? So that'll be sine inverse sine 60 over 1.2. How much you all got for R? Well, not really R, right? That should be theta 1. How much you got for theta 1? Theta 1 is how much? Yeah, how much all you got? Ijaz, what you got for theta 2? Wait, so what's the theta 1 all you? All you work it out? No, you got 49.2. Okay. I think Tion got that as well. Tion, you got 46.2 or 49.2? Oh, 46.2. Okay. Wait, you sure on yet? Check it back. It's over 1.2, huh? I see in 49 and I see in 46. What you all got? Yeah, I have 46.2. No round enough, right? So that's theta 1 is 46.2. 46.2, put in the calculator properly, right? Put brackets, something around it, right? Right, nice. Ijaz, what you got for theta 2? Theta 1 is 46.2. So what will be theta 2? Ijaz, you there? Ijaz. Some of you all forgot to fill out the Google form. Fill out the Google form, please. All right, Mr. Ijaz, I have your mother number. I'll be calling her shortly. All right. Let me see. Savira, what would theta 2 be? So far we got theta 1 to be 46.2. What would theta 2 be? Same thing, good, because of maths, right? All right, parallel lines, you have the 0 there. So theta 2 is 46.2. Beautiful. Right, but how we getting theta 3 now? What is happening from medium 1 to medium 2? Anuria, what is happening from medium 1 to medium 2? What is happening from medium 1 to medium 2? No, yeah, the ray slope. Okay, all right. So it's undergoing refraction, right? What is the refractive index that we're going to use here from medium 1 to medium 2? 1.25. Nice. Right? So you're using 1.25 and you're doing the same thing like here. Theta 3 will be sine inverse sine of the refract, which is 46.2 all over theta 3. I'm sorry, refractive index 1.25. How much is that? I just doing it too because I don't want to get the wrong value, right? 35.3 degrees. So we know theta 3 and theta 4. What would theta 4 be, Jaden? What would theta 4 be? Theta 3 is 35.3. Same thing, correct? Same thing, 35.3. Right, now for the bus brain part, theta 5. Easy though, but Anya said 60. Why you said 60 for theta 5, Anya? Because it is the reflected ray. Nah, I don't like that. That's not the reason why. Anybody know? The answer is 60. Anybody know why? Anybody knows why? Because it's back to air now. I'm looking for something else. Total, no, that's not how that would be total internal reflection, no. The ray came out, but that ray has a special name. And we said something about that ray. Refracted. Well, it is a refracted, but overall it has a name. It deviates. I'll call not everything, all you know. All right, focus on this ray and just this ray. Focus on those two rays, this one and this one. Right, it's the emergent ray. Right, and the angle of incidence is always equal to the angle of emergence. Okay? Right, they're always equal. Next one. Find the velocity of light in medium 1. Right? So you're using one of the formulas I gave you a little while ago, right? Should it be faster or slower in medium 1, Eden? Eden, should it be faster or slower in medium 1? Right, the speed in air is right here, right? 3 by 10 to the 8. Do you expect the speed here to be slower or faster? Slower. Okay, good. Correct. Work it out, message all the answers, please.
All right, what you all got there? Hey, wait, Colin, message nothing. Hurry up. What's the formula we using, Anya? Right, so we're using refractive index as speed in medium 1 over speed in medium 2. Speed in medium 2, that's this here, will be V1 on N. Right, V1 is what? They gave it at 3 by 10 to the 8, and the refractive index was 1.2. How much is that? 2.5 by 10 to the 8. Anybody else got that? 2.5 by 10 to the 8? Yeah. Well, you have to message your answer, Annalie. Right? Oh, okay. Well, you could just put 3 by 10 with that little slash thing, 8. All right, so good. That was one that we had to do. I'm trying to find EJAS. Anyway, I'll call you just now. All right, so nice. So that was just something I wanted to go over. That's not the actual question, though. I will look for it. Or we post it for you for homework. All right, so let us go back to our handout. Let's take a look at diffraction and interference, right? Right, so take a look at diffraction, right? If you look at that there, what you're observing is something called diffraction, right? Let me see if this simulation will work. Okay? Hold on. Let me see. It didn't work last time, but because everybody online, I could probably try this instead.
This one is interference. Oh, this is not it. All right, let me see if I can get it to work on the end there. Why can't I move this? All right, so what just here? So I am going to produce, there's a water wave generator, right? You all may have noticed this. You all may have seen this already. Not a generator, but you all may have seen water waves. Like if you all throw a rock into the ocean or into a body of water, what you will see is you will start to see some ripples, right? Those ripples are waves. So we're going to see now what will happen with those ripples when they pass through an opening. Watch it there. See how they curve up? That curving or that spreading is called diffraction. Right? That is called diffraction. And what will happen if I make it wider and wider and wider? That's the biggest. Right? You'll recognize it not as spread out as much. But if I make it really small, look how much more spread out it is. I'm gonna restart it. Yeah? Hold on. I'm gonna make it real small there. It's not just trying to make the wave a little bit smaller as well. All right, then alignment do that so good. I tried to make the wave a little thinner there. I don't know why. I just can't get to make it I can't get to press slow there, right? So you all had to pay attention, right? So what you say? I'm gonna produce the wave, and as the wave goes through the small opening, watch how it curves more. That curving is called your spreading, right? As opposed to if I had a big opening and then I would allow it to go, watch what will happen. It wouldn't curve as much. See that? It's not curving as much. Right? It's not curving as much. It's a little bit straighter. You mightn't see it so good, but it might be looking something like that. Fairly big waves, and I can't change the wavelength, but that's basically diffraction, the spreading of a wave, right? On the other hand, now, let's say I were to use double slit. That's one slit you see. Okay with diffraction. All okay with diffraction there, Chiran? You okay with the concept of diffraction? Yeah. Right. Watch what will happen here. Watch what will happen here when I change it from one slit. This is a slit, right? I'm gonna make two slits now. Tell me what you're observing now. What you will observe. Let's make them a little bit smaller. Right. This example kind of lame because I don't know why I can't adjust the. Yeah, I can't adjust the wavelength. Oh, it's a little bit smaller. Anyway, what will happen here? I can't even press slow on this stupid thing. What you will observe now is diffraction happening at 2 points. And then when those waves undergo diffraction, they kind of intersect it. Right? I'm not sure if you're seeing that so good. I'm gonna see if I could try a different one, right? There's one with lasers. All right, this one you might see it better. All right, what you see here? why we can't change it to lasers? Hold on now, yeah? Y'all see the laser option anyway? Instead of this stupid water thing. I'm trying not to use the... There's one with lasers. You seen it there? You seen the option? In the box. On the right.
So it's below separation between the third, yeah.
Okay, all right. Thanks. I didn't see that, but I can't press anything below normal. My screen block up there. All right, so watch this here. If we produce waves at the same time, oh crap, I didn't produce at the same time. All right, that kind of late. I want to produce them at the same time. Right. How are we doing that? Right. So what you will see there is that the waves intersecting, right? Because the waves coming through at that same point there, the waves undergoing what we call interference, right? I'm gonna try it back with this one here, where it slips. Is there the screen option? Yes. All right, so watch this here, right? I'm gonna just make the slip separation a little bit bigger. Right, so as the ray comes out there, they're undergoing diffraction in both of them, and those diffracted rays, they're meeting. Right, this is it. Right, and because the rays, undergoing diffraction, right, they're undergoing diffraction out of these slips here. So they're undergoing a diffraction, but then at a particular point, they're undergoing interference. Right? Look at the red. So each of the red, they kind of intersect in each other. And see these regions here where they intersect? That is called interference. And there are two types of interference. There is constructive interference and destructive interference. Exactly what the name suggests. Destructive means that the waves cancel out each other. So you see here and here, there are no waves there. Those are dark fringes. Seeing that? And then in between, you're seeing bright fringes. So you're seeing bright. This that you're observing here is called a fringe pattern. And the fringe pattern is a mixture of light and dark. Light and dark. You're seeing that? So what you're observing here is an interference pattern. The waves undergo diffraction here, and then they undergo interference. Right? You have constructive interference, right? Constructive interference producing all these bright fellows here. And destructive producing all these little dunce heads here. So all them dunce heads, right? That producing destructive, are produced from destructive interference. Right? You also see the difference between interference and diffraction. Lindsay? Annalie? Are you okay there? Right? Of course, I could change color. Of course, hold on. I could change the color. What to do? Let's change it to red light. Let's use double slit. I want to see the screen. Interference here is where they intersect. And there are two types of interference, constructive and destructive. Right? I forgot the values I used, but right. Hey, watch this one here. Using red light this time. See, they're intersecting again. They're on a good diffraction. And now on the screen, you're seeing red and black. All right, you could change it to purple to blue, same thing. They intersect and you will see blue and black. Right? Everything you're observing here is your interference pattern. And the first guy to do this and observe and explain was a guy named Young. He was kind of old, but his name was Young. This was Young's double slit experiment. He did something just like this. All right, so that is your interference and your destructive and your diffraction simulation, right? Of course, we need to figure out, okay, why it is it canceling off at some points, and why at some points it's not canceling off, right? That is where your little theory will come in, right? We have to know what is happening. Why all of that happening? Why do run away, run away? Right, so right, diffraction. We talked about this already, right? Your homework, you had to learn all these rays here earlier. This is called the EM spectrum, right? You have to learn all the rays and the order from the longest to the shortest wavelength, right? These are a special type of rays called the electromagnetic spectrum, right? Probably the most useful for us as well, right? Yeah, you have all these waves, right? You have from radio waves all the way down to gamma rays. You have to learn that spectrum. Just like how you have white light have a spectrum, and technically white light belongs to the spectrum as well. If you look here, this is visible of white light. Then you have infrared on one side, bulb on the next side. All right, you have to learn those wavelengths and their uses, right? So I'll give it that. I'll add that to Kahoot next week. Right, so let's take a look at diffraction, right? Diffraction. Right, so diffraction occurs when a wave passes through a narrow opening or aperture and thus spread out over a large area as it continues to progress. All waves can undergo diffraction, right? You'll recognize again that the smaller the opening, the more it will spread out, right? It is difficult to observe diffraction of light because of the small wavelength. Special equipment must be needed for the observation. And that special equipment is called a diffraction grating, right? There's something that you have in a microwave. If you pass light through a diffraction grating, you'll be able to split it up. Theories of light, you have Isaac Newton, right? And you have to know this, right? Isaac Newton basically said that light is a stream of particles, right? Called corpuscles. Huygens, right? You might name it Christian. It's Huygens. Light is transverse, not particles. And then there was a guy named Young. Light waves can undergo interference. And then the one person that changed the way they viewed physics on the whole, right? He created or he started what we study today called the modern physics era. That was Albert Einstein. He said, you know what? Light is not made up of waves alone. Light has waves and particle properties. So imagine the light that coming from your ceiling right now, right? From whatever bulbs you have. That light has particle properties, right? And Einstein was able to prove and show that calculation, that light has particle type properties, and he called it photons, right? You all do an experiment for those who do physics in Cape, called the photoelectric effect. And the only way they could have explained that back in the 1900s was by saying, okay, now light had to have some other property making it behave differently, right? And Einstein came up with it, and he said that that property was particle. So he said light had two properties, particle and what they knew before as waves, right? So you have to know all those little theories there, right? Einstein also came up with the photoelectric effect, which he won a Nobel Prize for. The photoelectric effect is a phenomenon that produces electrons when light is shone on a metal plate. Ideal examples of this are solar panels and digital cameras. In digital cameras, photons have different strengths, which produces variations of brightness and color to translate the photograph image, right? And then we have interference, right? Interference occurs when two waves, right? And if you want, you can read up on or even take a look at the simulation of the photoelectric effect. So you would see light behaving differently, right? Interference occurs when two waves superimpose with each other to form a resultant wave that might either raise or lower the amplitude. There are two types of interference, constructive and destructive. So here's what happening here. Whenever you have a crest, line up with a crest. So you have a wave, and on top of that wave, you have a next wave intersecting, right? Let's change color. But the crest and the crest and the trough meeting up. What will happen now is that you will add up what's going on. Superposition is like adding up the displacements at different points. And if I add it up, I'll get this super big wave, right? That's called a constructive interference. So everything is seen here. This amplitude plus this amplitude is this big amplitude here. The wave is twice as big, right? But whenever you have a crest meeting a trough, think about it. If you have an amplitude of 2 meeting an amplitude of -2, when you add it, you'll get 0. So you have this straight line, which is destructive interference. Okay, right? These waves here are said to be in phase. These waves here are said to be out of phase. Right? Out of phase just simply means this and this meeting half a wavelength after. Right? Let me just explain that concept here, right? So you have a wave looking like this, nice and dandy, right? And then you have a next wave. But that next wave didn't start here, right? That next wave starts a whole half a wave. So when this wave, the first wave, travel half a wave, this fella here now started. Right? So it's out of phase by half a wave. And you see a trough meeting a crest. When you add up that, you get 0. And then you have this canceling off. And as you remembered in our experiment, you had the same pattern here. Crest and trough. Crest and trough. You had the same pattern here. Right? Sorry. You had the same pattern here. Light and dark fringes, right? Okay? So that is your interference. Right? And well, you have some things show you that light travels in straight lines and things. Right. A physics notebook wouldn't be complete without this diagram in it. Right? But here's what you're going to do for me. Right? You can start it now, so you wouldn't have nothing to do for homework. Remember, we have no physics this Saturday, right? This Saturday is no physics, right? Right? Here's what you're going to do for homework. Let me see if I can get a blank page. Hold on, and please try it. Let me say right here, like a pass there, right? So you have waves being produced here, right? So you have your slips, and you have waves being produced. What you are going to do, using a protractor and a ruler, you're going to draw a crest, right? And then change color, or you could use broken lines. I would change the color. After that, I want you to draw a trough. And then do a crest again. And then do a trough. All equally spaced, right? And then do it on the next side. Same thing. Crest, trough. Crest, trough. Right? And what you are going to do, you are going to point out, or just, you could draw a line will be good enough. You are going to point out all the places where the crests meet the crests, right? Remember, the brown is crest, and the blue is the trough. When the crest meet the crest, what will happen again? When crest meet crest and trough meet trough, what is happen again? Constructive or destructive interference? Constructive. Good job, Nuria. Thanks for listening, Nuria and Anya. Right? So you're going to draw a line. And that line will indicate constructive interference. And that is why you will observe a bright fringe there. And then you look for where the crest meet the trough, which will be right next door. And that will be a dark fringes. So you have to draw it on your use the whole use a whole page, right? And I want you to use a compass to get the arcs, and of course a ruler to measure of the distance between crest and trough. And let's see if a diagram will be purple. Mine's looking real good, by the way. Mine's looking pretty good. And Severe, mine's looking real good right here. Right? Because you're actually getting to see crest and then trough. So that is not hard to do, Anya. That is not hard to do. You're drawing two lines so, and you do that little thing so, and a little thing so. That's all. You just have to be precise. All right? Take your time, and I want you to do that for me. You see, your book wouldn't look like a physics book if you don't have that diagram. You have to have that diagram. Right? And that is basically showing you interference, and it shows you where and how the diffraction pattern is produced. Okay? So I want you to do that for homework for me. You can always look back at the last part of the video and see what I did, right? I'll give my little views there too. Okay, so that brings us to the end of wave phenomena. This theory thing real important here because sometimes people forget this theory. I don't know where it's going, right? People kind of forget these little theory things here about light. Can't remember where it goes. Oh, look at here, theories of light, right? You need to remember those little things. So when you see Huygens, you know what Huygens said. All right, so that's your little piece of homework I want to give you together with reading up on EM waves, and you can probably even read up on some, right? EM is transverse, and sound waves is longitudinal waves, right? We have to take a look at those two things next day, right? And then we look at lenses. You need graph paper. So work with graph paper next class.